Okay, it's time to finish up Chapter 3, Section 2, Polynomial Functions. And we'll start this with the intermediate value theorem. The IVT tells us of the existence of real zeros. This is an existence theorem. It might not exactly tell us how to find the zero, if it is possible to find it at all. But we do know that such a number is out there. You see quite a few existence theorems in calculus. The idea behind the theorem we're going to illustrate here as we go along. So here is the intermediate value theorem. Copy this down in your notes. I left you a little space there to the left of your empty graph. And the IVT states, let f be a function. If f of a and f of b have opposite signs, then there exists a point C between a and b such that f of c is equal to 0. Okay, it might be a little confusing, but let's parse it into pieces and create a graph as we go and see what happens. It's not really that scary. Okay, let's see. We have 2 points, A and B. So we'll call this point A. Here's point B. That's our interval. And it says f of A and f of B have different signs. Well, maybe when we plug A into the function, it gets mapped down here to a low part on the y-axis. This would be f of a, and notice that we are negative. We're below the x-axis. And maybe when we put b in the function, it gets mapped up here to this height on the y-axis, and that's f of b, and it's positive. And again, I could have reversed those. I could have made f of a positive, f of b negative. The big thing is, I got an extra 0 or O in there. The big thing is these two values have opposite signs. One's positives, one's negative. Our theorem says then there exists a point C in between A and B such that f of C equals 0. Think about it this way. Is it possible to connect the dots A and B without crossing the x-axis? This is point A and this is point B. Can I connect the dots in this interval without crossing the x-axis? I could go up real sharp. I got to cross the x-axis. I could head straight for point B. Got to cross the x-axis. I could wait till the very last second possible and cross, and then I still got it. Well, that's not really a function. That's a little better. There's no way to get from point A to B without crossing the x-axis. We have to do it at some point, so we know there exists that point C somewhere in there. Here's point C, or maybe here's point C. Somewhere we have to cross the x-axis. Again, that only happens when f of a and f of b are on different sides of the x-axis. One's positive, one's negative. So here, for example 8, show that this polynomial has a real 0 between 2 and 3. All right, well, let's check our endpoints. Our interval is 2, 3. So let's check our heights. F of 2. That's going to be 2 cubed minus 2 times 2 minus 5. Or 8 minus 4 minus 5, which is negative 1. And of course, it's obvious that's negative. And the other endpoint is 3, f of 3. That's going to be 3 cubed minus 2 times 3 minus 5. So that's going to be 27 minus 6 minus 5, which is 16. And it's positive. Okay, because one's positive and one's negative, by the IVT, by the intermediate value theorem, there must be some number between 2 and 3 that when we plug it in here, it's going to exactly equal 0. Now, if this was a nicer polynomial, we could just try to factor it and break it down and see where that 0 lies. Another way to do it would be with the TI-89 graphing calculator. Maybe in class we'll have time to break them out. And there we'll go to the y editor. That's green diamond F1. And we type in the function x cubed minus 2x minus 5. And then we can go to the graph on the graph screen. And then hit your F5 key. And that'll bring down a drop-down menu. And you can choose the option 0. When you choose the option 0 down in the lower left-hand corner of the calculator down here, it'll say lower bound. Type in your left endpoint 2 and hit enter. And then it'll ask for the upper bound. Type in the 3, the right endpoint, and hit enter. And it'll spit out down at the bottom an x value of approximately 2.09455 and dot, 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 depending on what display you have your calculator set at. So there is a 0 in between 2 and 3. It's, going to be impossible to find it without the calculator or some other more advanced method. All right. The turning points of a polynomial. The graph of this fifth power polynomial is shown in the figure. The graph has 4 smooth turning points. Remember, polynomial we always have smooth curves. So here is our fifth power function, and let's count the turns on the curves. Well, here's 1 curve, and then we come down, and here's 2 curves, and then 3 curves, and then 4 curves, and then we're off to our end behavior. So at each turning point in the figure, the graph changes direction from increasing to decreasing or vice versa. The given equation has 5 as its greatest exponent and is therefore a polynomial function of degree 5. Note that the graph has 4 turning points. In general, if f is a polynomial function of degree n, then the graph of the function has 1 less, n minus 1, turning points. The figure again illustrates that the y-coordinate of each turning point is either a relative min or a relative max. Remember when we were doing parabolas and talking about mins and maxes. So this wouldn't be an overall max, but it's a relative max. It's maximum to the points right around it. Here's another max. It's a local max because the points right around it are all lower. And then we got a couple local mins. Here's a min. It's at the bottom of a valley. And here's another one. Without the aid of a graphing utility or the knowledge of calculus, it's difficult or often impossible to locate these turning points of polynomial functions of degree greater than 2. If necessary, test values can be taken in between the x-intercepts to get a general idea of how high the graph rises or how low the graph falls. For the purpose of graphing in this section, a general estimate is sometimes appropriate and necessary. So here's some steps to graph some polynomial function. 1, we're going to figure out the end behavior with the leading coefficient test. Step 2, find the x-intercepts. Set the equation equal to 0. Solve the resulting polynomial. If there is an x-intercept at some value r, as the result of, you could put it in the form of a factor x minus r to the kth power in the complete factorization then. If that exponent is even, we have even multiplicity and the graph's going to touch and turn. If that multiplicity is odd, we cross at that point. If that exponent k is greater than 1, the graph flattens out near that point. Find the y-intercept. Plug a 0 into the function and see what comes out. If possible, use symmetry to help draw the graph. Remember, y-axis symmetry. Y-axis symmetry was for even functions, or origin symmetric functions. Those were the odd functions. Use the fact that the maximum number of turning points is n minus 1, where n is the degree of the polynomial function. Check to see if your graph is drawn correctly. Okay, let's try it out here. Example 9. Graph this polynomial function. Step 1. End behavior. Leading coefficient test. So what's our end behavior here? It's positive, it's 4th power. That means up to the left, up to the right. 2, we want to find our zeros, our x-intercepts. Set this polynomial equal to 0. X to the 4th minus 2x squared plus 1 equal to 0. Well, it's a type of quadratic. I can see my x to the 4th. That's an x squared and an x squared. The factors of 1 are 1 and 1, and to get a minus in the middle and a plus when I multiply, it has to be 2 negatives. And each of these breaks down farther. X minus 1, x minus 2 for the first difference of squares, and then another x minus 1. Oop, back, that's supposed to be a 1. X minus 1, x plus 1 for the first difference of squares, and then another x minus 1 times x plus 1. Equal to 0. So if we collect our like factors, we're going to have an x minus 1 quantity squared and an x plus 1 quantity squared equal to 0. So we have 2 zeros. We have x equals 0 at positive 1, and that's multiplicity 2. And then when we set this factor equal to 0, we're going to have a 0 at negative 1, also of multiplicity 2. That means touch and turn. Touch and turn at those zeros. So let me get that out of there and move this up. Step 3 was the y-intercept. 3 is y-intercept, and that is f of 0. So let's see, I'll plug in a 0 for this term. That 0 to the 4th is 0. 2 times 0 squared is 0, so my y-intercept is 1. Step 4, do we have symmetry? I see my exponents are 4 and 2. Those are even. And remember, constants just slide you up and down the y-axis, and that does not destroy y-axis symmetry. So we do have y-axis symmetry due to our even function. And step 5, and we should have n minus 1 turns. Our 4th power function is going to be 4 minus 1. So that should tell us our graph will have 3 smooth curves, 3 smooth turns. So let's see if we can put all this info together and come up with a graph. So leading coefficient test gave us our n behavior, up to the right, up to the left. Our x-intercepts were 1 and negative 1. Our y-intercept was positive 1. We have symmetry around the y-axis, and that looks good, because we're going up to the left and the right. Our x-intercepts are also symmetric around the y-axis. We're crossing here at 1. So let's see if we can put this graph together. Our end behavior is up to the left, so we're sort of coming down as we come toward the graph. And we know we're going to hit at negative 1, but not cross. We're going to touch and turn. And then we got to cross the y-axis at 1. And then again, we have to touch the x-axis again at 1. And then touch and turn, and we're up and to the right. So it looks like a W. My graph isn't drawn very well. My graph isn't symmetric when we know it's supposed to be. It would probably be, let me give myself a little better shot at it here. Maybe a little more something like this. Again, we're not super accurate. We could throw in some more points and get a better idea. We're just coming up with a good sketch of the graph. And there it is. Not too shabby. Okay, I think we got one more example. Example 10. And here they were nice enough. At least they gave it to us, and it is fully factored. Look at that. They broke it up into some nice factors for us already. So let's see. 5 steps. 1. End behavior with the leading coefficient test. Our leading coefficient is negative. Our function is what power? Let's see. Second power, first power, so it's odd. Third power. Negative and odd means up to the left and down to the right. 2 are zeros. Again, they did give us to us nicely factored. So here, x minus 1 equals 0 at x is 1. And that is multiplicity 2. And that means we're going to turn around. Here is another 0. X plus 2 equals 0. So we'd subtract 2 from each side and get x is negative 2. That is multiplicity 1. So we're going to cross. Let's see. Step 3, y-intercept. See, we're going to plug in a 0 for all x's. So this equation starts with a negative 2. And then we're going to have a 0 minus 1, and that's negative 1 squared. And then we're going to plug in a 0 for this x and get 0 plus 2 is 2. And that's to the first power. So we square the negative 1 and get a positive 1. Positive 1 times 2 times negative 2 is going to be negative 4. Step 4. Do we have symmetry? Well, I guess we're going to have to connect the dots that we already have first. Our zeros are at positive 1 and negative 2. And our y-axis intercept is at negative 4. Notice that these are not spread nicely around the y-axis. So it's not going to be y-axis symmetry. And it doesn't look like origin symmetric either. So no symmetry. That's not going to be much help, but that's okay. No symmetry. Step 5, we should have, see, our exponent was third power, so we should have 2 smooth turns. Let's back up. Did we check our turns here? We were supposed to have 3. So let's see, here's our first smooth turn 1, and then 2, and then 3, and then we were off. Okay, almost forgot that part. Okay, let's see here. Our end behavior, up to the right, down to the left. So let's start working left to right. I'm going to be up here in the second quadrant, coming down, and I know when I hit -2, I'm going to cross the x-axis. So at -2, I'm going to cross, and then my next thing is I got to head for the y-axis, and I know I got to cross the y-axis. And then after I cross there, I'm going to head for my next 0 at x is 1. That had the multiplicity of 2, so there I'm going to touch and turn around, and then I'm headed off to my end behavior down to the right. And we should have 2 curves. Here's 1, and then we have 2, and there's our graph. Beautiful. All right, 3 for you to try on your own. Number 10, I should have gave you a little bit deeper on the y-axis. I shouldn't have cut that out. Or what I should have done, I can do this for next year, I guess. I'll drop that graph in for when we do that one. All right, so pause the video and try those practice problems out, and then fire it up and see if you got them right. I told you to pause the video. Pause the video. Try them on your own. Okay, show that this polynomial, f of x, is 3x squared minus 10x plus 9. Actually, I like doing it like this. F of something is 3 times that something cubed minus 10x plus 9. And we want to see that it has zeros between -3 and -2. So f of -3 is going to be 3 times -3 cubed minus 10 times -3 plus 9. Watch your order of operations. We do the exponents first. -3 cubed is -3 times -3 times -3 is -27 times this 3 is a -81. And then we have a -10 and a -3. Those multiply to a +30. And then plus 9. And if we add those all up, what do we get? -42. -42. Again, note that it is negative. F of -2 is going to be 3 times -2 cubed minus 10 times -2 plus 9. See, our -2 cubed is -8 times 3 is -24. If we multiply the -2 and -10, we get plus 20 and then plus 9. So these add up to 29 minus 24 is +5. Because there isn't a sign change from positive to negative, by the IVT, the intermediate value theorem, there has to be a 0 between -3 and -2. Didn't tell us how to find it, but we know it's there somewhere. All right. Use the 5-step strategy to graph this one. So, step 1, end behavior. It's odd and it's positive. So by the leading coefficient test, odd and positive, up to the right, down to the left. 2, x-intercepts. Where are the zeros hiding? Well, we're going to take this and factor it. Factor out an x squared, and you're left with x minus 3. So we have a 0 here at 0. X equals 0. That is a multiplicity of 2 because it's x squared. So we're going to turn around that 0. If we set this equal to 0, x minus 3 equals 0 means x equals 3. That is multiplicity 1, and we cross at that 0. Step 3, y-intercept. That's an easy one. Plug in zeros for both of those x's, and you get 0. Y-intercept, 0. We are going to go through the origin. Step 4, symmetry. Notice the exponents. 1 odd and 1 even exponent, so that is no symmetry. Step 5, when we're all done, when we're done with the graph, we should have 3 minus 1, or 2 turns. Let's plot some points. End behavior, up to the right, down to the left. X-intercepts at the origin and at 3. At the origin and 3. And remember, at the origin, we're going to touch and turn around. And then we're going to cross at 3. So here, we're actually going to cross. At the other one, we're going to touch and turn around. All right, so our end behavior tells us we're going down. We're down here, and we're going to head up toward the 0, and we're going to hit it and touch and turn around. And then we're going to be heading back down here. We know we got to cross the x-axis again at 3, so we're going to come up and cross. And then that takes us up and off to our end behavior. So there's our function. Oops, that was supposed to be an eraser. And another graph one here. This one was fully factored for our convenience. So let's see. Yeah, I'll still write the steps down. 1, leading coefficient test for our end behavior. It's positive, and it's second power and first power, so it's third power, odd powered, positive odd powers, up to the right, down to the left. Step 2 are zeros. If we set this equal to 0, we're going to get x's -2, and that is multiplicity 2, so we're going to turn around. Our other 0 is right here. X minus 3 equals 0 means x is 3. That is multiplicity 1, and we're actually going to cross. So at -2, we're going to turn around. At positive 3, we're actually going to cross. So I'll go like that. Step 3, y-intercept. We're going to plug a 0 in for all the x's. So the 2 goes first. And then we're going to have 0 plus 2 is 2, and that's squared, so that's a 4. And then our next set of parentheses is going to be 0 minus 3 is -3, and that's to the first power. And if we multiply that all out here, we're going to get these two multiplied to a -12, -24. So that is, of course, going to be a little bit off the graph. We'll go down and off. We'll just rewrite this as -24, so we can at least see the graph. Our axis won't be to scale. Step 4. Just judging by these two x-intercepts here, we're not going to have any y-axis symmetry and neither origin symmetry, so no even or odd symmetry to speak of. For number 5, it was a third power function, so we're going to have 2 turns, 2 curves on the graph. So let's see. We're down here heading down in the 4th quadrant, so we're headed back up as we move left to right on the x-axis. I know at the -2, 0, we are going to hit and turn around, and then we got to go way down and cross the x-axis at -24, and then we're coming back up and we cross at 3, and we're to infinity and beyond. Let's check our turns. We should have 2 of them. 1 turn right there, 2nd turn right there, and we're off. Alrighty, that was fun. To have more fun at home, right there, page 361, got a half a dozen of these polynomials. Probably most of them you got a graph. Just follow right along with the examples and the huddle problems. If you don't have your book with you, here are the directions, and then here are the problems. You can just pause the video and copy those down. So enjoy, and I'll see you in class.